this greedy algorithm, it could be highly suboptimal. Might not be the best decision to do overall. So what's the next idea over this? It's something that that is called batch matching. So what you do in batch matching, you wait for a little bit. So when you request, you don't get assigned it right away. You see the app turning for a little bit before you get your assignments. What the app is trying to do is trying to get as many requests as you can. And the moment when you have like enough requests, or like the moment where you reach your upper bound in terms of the waiting time, then you make the assignment. So in this example, in this toy example that I just explained to you, well, the best thing is, you wait a little bit, you see this request too, then this first request would be assigned to this driver. The waiting time is only 4 minutes. And then for this one, you get that first car that was assigned to the first request. Now we're going to assign it to the second request, and the waiting time is 4 minutes. So in this toy example, as you can see, the total waiting time is 8 minutes. So we've increased for the first request by a little bit, but decreased a lot for the second request. And overall, this, if you look to the average waiting time in your graph, is lower than the output of the first algorithm. Is that clear? So what do you do in general? So in practice, you don't have like just 2 requests. You might have like, in big cities, you might have thousands of requests. You're not gonna do that by hand. There is an algorithm that runs behind the app. There are researchers, there are scientists that work on developing those algorithms in order to make this matching decisions. So in general, what do you have? So you have a bipartite graph with the clients on one side, okay? And then the drivers on the other side. And so you construct this bipartite graph. These are requests, and these are your available drivers. We define the weight of each edge. For simplicity, now let's think about the weight. You just want to minimize the distance or the waiting time. These are proportional, so let's use one of them. Let's think about the distance. I to j, so the weight of the edge I to j is dij, which is the distance between I and j. So you want to find an assignment for each of these drivers that minimizes the average distance of the matching, or like the total distance. These are the same thing in the graph. How do we do that? Who's familiar with optimization in general? Good. Maybe, well, you're organizer, so cool. So the field of optimization. So optimization is, it's a field under, I would say, again, the umbrella of operations research, mathematics, computer science, where you would like to maximize an objective function, and you have some variables, and these variables need to satisfy some constraints, okay? Maybe at high school, you've seen maximizing a function, right? Maximize f of x in this domain, right? So this is like a single variable function. On the variables. So variables need to satisfy something. So I'm gonna give you this, this is an optimization problem. I'm gonna go through this optimization problem slowly. So here the objective, the decision variables are xij. Xij are binary decision variables, which means they take value 0 or 1. Xij is 0 or 1. What does that mean? It means that xij is equal to 1 if we assign rider I to driver j, and 0 otherwise, okay? So it's a summation over all drivers, summation over all riders, dij times xij. So which means that if you assign rider I to driver j, then xij is equal to 1. you have to put some constraints. What are the constraints? Is that for each rider, over all I in D. Okay? So these constraints, because these are all binary variables, driver that will be assigned to the rider. Okay? So here I'm assuming that the problem is less or equal. Okay? If I cannot satisfy all the driver. And then my objective is to minimize the total distance. Okay? Okay, I'm getting to that. Perfect. So in polynomial time. Okay? So what does that mean in polynomial time? It means that's exactly what your friend was referring to, the complexity of the problem. You want to do a certain number of closely to what you are saying, the platform might not be interested in the waiting time, might be interested in the expected revenue they're going to collect from the platform. So the weight could be like how much revenue the platform will collect if you match I to J. Okay? And that's another objective function. There's another, see some other hands.
Maybe you might be thinking about the traffic for riders in order to get to riders, like the road between the
Yeah, that's a good point. So you might include the traffic, but that's, you can also include it in, instead of saying DIJ, you can say TIJ, the time that takes between I and J, and these coordinates can be given by Google Maps and including the traffic. But that's a good point. Let me tell you something. So actually, no one knows the exact objective function that Uber or like these big companies use, unless you work there. There are many other factors that you need to be considered. But what we know as researchers is that the mathematical problems that is solved is the following. You are maximizing some objective function of the following form. You are maximizing the weight of your matching. This is the same constraint that we had before. Okay? So the problem is a maximum weighted matching in a bipartite graph. I'm just changing the mean to max, and then I'm changing, instead of distance, I assign a weight to the edge ij, and when I maximize the total weight. This is again a problem that we can solve in polynomial time. But what is the weight? The whole story is about this. Wij, each platform defines Wij in a different way. This is usually given by some machine learning models. What does it try to incorporate? In fact, the moment when you going to make a request, right? It's not clear that the driver is going to accept. You might get assigned to a driver and you might cancel, right? The platform also might be interested not only in the distance, but as well in the cost or in the revenue that you generate. So all of that are incorporated in this Wij. So think about Wij as the probability that the matching would happen between I and J. So that would also include, the cancellation probability, as well as the benefit of the platform from matching to I and J. So this is the math problem, and this is like the application. The third idea is the following. So we talked about greedy algorithm for matching. We talked about batched matching and the minimum cost perfect matching, as well as the max weighted matching. The third one is the following. We have a lot of data nowadays, okay? We do have a lot of data. So we can do batch matching. We can do batch matching and try to optimize the objective function for the current batch. But I might go back to the same point that Abdul Qayyum said at the beginning, that then we might be optimal for the entire current batch, but might be suboptimal for the next one. We can use data, historical data, to try to understand what's going on for the next batch and solve not only a single stage problem, but a two-stage or a multi-stage problem. And there are a lot of recent papers that are trying to do that, and I'm going to try to explain to you briefly, some of this is recent research. So the way how I wanted to structure this part, I started by a very classical matching problem, right? Current application. I told you about these algorithms that are used to solve matching. This has been known for decades. And then I'm going to finish this part with some of the most recent algorithms, just to give you a glimpse of the current research that is conducted in this area. So the question is, how can we use partial information about future demand to make better overall matching decision? I'm going to talk about a very simple model that I developed in this paper with my co-authors here. This paper has been published a few years ago. But it's called two-stage robust matching. Well, no one knows the future. If we know the future, we're good, right? You're gonna make a lot of money if you know the future, right? You don't know the future. But what do you know? You might have some understanding of the future. You might try to model uncertainty, right? The future uncertainty through something. What is this something? There are two classical approaches to model uncertainty. There is something called stochastic optimization, where you're thinking about probabilities. You're thinking about probability distribution to model the future, right? You might say tomorrow is gonna rain with probability 50%, and it's gonna be sunny with probability 50%. You're giving me a distribution of what's gonna happen tomorrow, maybe based on historical data, okay? The other thing is, if you want to be conservative, if you want to be robust, you want to hedge against the worst case, there is something called robust optimization, where you are going to give me a set of possible scenarios that could happen tomorrow, right? And the goal of the optimization problem is to hedge against the worst case scenario. So you can give the scenarios as explicit scenarios, or you can give them as implicit scenarios where the future scenarios will be satisfied through some constraints. You're going to understand that in the next slide once I go into more detail. So as I said, robust optimization is more conservative than the stochastic approach than using probabilities, but it's easier in the sense it's easier to construct scenarios than constructing probability distribution. If you want to use probability, you need a lot of data, especially when you're thinking about a high dimensional distribution probability. So this is the dynamics of the model. Again, a bipartite graph, okay? A bipartite graph. On one side, you have the drivers, and then on the other side, you have the riders. Thank you for all the pictures, by the way. So you have the riders on the other side. Now, what we will do is that, remember, we have a batch that we need to match right away. This is called R1. I'm going to call them the first stage riders. We need to match them immediately. But on the top of that, given my historical data, I might have some idea about future requests. And so here, I will denote that. I will use R2. This is a set of possible second stage riders. Possible second stage, which means that the scenario that I will observe in the second stage, maybe in 2 minutes, would be something that would come from this set, from this location. Okay? So I would know that, after 2 minutes, there might be some requests, but I don't know which one. It might be like 2 requests from here, 1 from there, or 2 from there and 1 from there. There is a set of scenarios that could happen. And I would like to solve the matching. What I was doing in the previous slide, I was ignoring R2 and solve the matching between R1 and D using the approach that I showed you, okay? But here I would like to include that as well. So these are the notation. Dij is again the distance between I and J in my graph. We're just gonna go back to the distance metric, okay? Okay, so first batch of riders have requested rides and need to be matched to some drivers immediately. Now, how to model the uncertainty in the second stage? So one way to set uncertainty, you have a set of scenarios, S1, S2, Sm. These are possible scenarios that you've constructed from historical data. Another way is implicit scenario. You know the universe of riders, you know the potential location where the requests are going to come from, but they're not going to come all at the same time. There is at most k of them that's going to be materialized. So the size of S is at most k. So there will be at most k requests. I don't know from where, but I know the universe of them. And my objective function is the first stage matching cost. That was my previous objective function, but now I add a second term on it, which is the worst case matching over all possible scenarios. Okay? So I'm trying to kind of include the uncertainty about future requests into my optimization problem to be more efficient. Again, my goal is trying to give you a glimpse of several objective function and several matching problems that has been studied. So we've seen the minimum weight and the maximum weight. So here I want to talk about something which is called the bottleneck matching. So sometimes you're not interested in only in the average, but you are interested in minimizing, be careful with me, minimizing the maximum weight, in the sense that I don't care if my if my riders wait 1 or 2 minutes or 3 minutes, right? 1 or 2 minutes does not make a difference, or 2 and 3 does not make a difference. But what makes it different, I care about the maximum waiting time, let's say, should not exceed 5 minutes. I want my worst case, rider not exceeding a certain threshold. And that threshold is called in English the bottleneck. So bottleneck matching is find a feasible matching, right? Such that the maximum weight is minimized. So let's look to this objective function in the context of two-stage matching. This might be the slide where I put the most mathematical formulas, but I'm gonna go slowly through that, trying to explain those terms. So the first term here is the cost of the first stage matching. So my first stage matching between the drivers and R1. R1, I need to match them immediately. The objective is a bottleneck matching, Dij, Xij. Okay? And so each rider needs to be matched. Sum of Xij is equal to 1. Okay? What about the second stage? So this is Z is the cost of the second stage. What I want in the second stage is for any scenario, I want to find the decision variable. This is a matching such that the cost of that matching is smaller than Z. So that Z here represents the worst case second stage cost. And of course, each driver can be used at most once. You can either use it in the first stage to match R1, or in the second stage to match a rider in S, in one of the scenarios that's going to be materialized. And then if the scenario happens, then you have to match each rider in that scenario. So for each J in the scenario, you need to find the driver to match it. So that's why the sum here is going to be 1. Again, Yij and Xij are binary variables. That tells you whether you match I to J. Okay, so this is the optimization problem. I'm not going to go through more details on this optimization problem here, but this is a complex optimization problem. This is not even an integer program. So you have the integer variables, but the constraints here are not linear. You have this for all S. There might be exponentially many scenarios. And we need to develop efficient algorithm to solve this problem. And this is like some of the research that has been done currently is to solve these two-stage and multi-stage and online matching problems, both in the stochastic and robust setting. So I'm going to skip some of the stuff here, and I'm going to try to summarize some of our results on this problem. So unlike the previous problem that I showed you, which we can solve in polynomial time, this problem we can show that it is NP-hard. NP-hard, that means there is no polynomial time. You can show mathematically there is no polynomial time algorithm that can solve this problem unless, unless NP is equal to P. So unless NP is equal to P, right, there is no polynomial time algorithm that you can solve that. So when you're facing this issue, you have two solutions. You either develop an approximation algorithm, you're not going to be able to solve the problem exactly, or what would be the second solution? Show NP is equal to P. Okay? So I chose the first one. So to develop approximation algorithm for this class of problems. So this problem is NP-hard, and the goal of the research is to approximate solution, but with theoretical guarantees. You show that, so here for the set of explicit scenarios, we give a constant approximation for two scenarios. For implicit scenarios, we give another constant approximation. So these are like, you have to develop new ideas based on like some combinatorial ideas, something that is based on integer programming and broadly on optimization to design algorithm for solving this problem when the problem is actually NP-hard. If you are like from the school of like computer science, where the goal is to design polynomial time algorithms. So these are some of the, our results on the hardness. We show that we cannot solve the problem in polynomial time, even given an approximation of 2, a factor 2 for this problem. So which means we need to design approximation that's, at least at most is going to be like 2. And this is like some of the, our results. I'm not going to go through the details because I do have other materials that I want to talk about. But to finish this first part on matching in ride sharing, so with my research group, we deployed this algorithm to solve a matching problem using a data set from this city in China called Shenzhen. So there is a data set that is available online that gives you data for all taxis in the city of Shenzhen. The data tracks the taxi ID, the time, the location. So these 2 things: longitude of the taxi, the speed, the direction, and whether it's occupied or not. So in the sense, you can have a snapshot of all the drivers that are available, as well as when this column he switches from 0 or 1, that there is a request for a ride, and then we compare the 2 approaches. The second approach, which just look to a greedy algorithm for the first batch that ignore completely what could happen in the future. And the second approach, which is what I presented to you, you look to the historical data, you try to have an idea about the uncertainty in the future, you model that through explicit scenarios, and then you solve the problem taking into account the uncertainty in the future state, and you compare both approaches, and the results are given in these 2 columns. So you can see an improvement here, 50%, 30%, 50% in terms of the waiting time when you use this 2-stage algorithm instead of using a single-stage algorithm. So the numbers differ from an example to another one, but overall in this paper you can see an improvement of around 30% in terms of the waiting time by leveraging first historical data, and second thing, trying to develop good algorithms to solve this matching problem. Any questions about the first part before I go to my second one? And at the time, I'm going to take some water. Please. Yeah. Maybe you should have a mic, yeah. Nu'man.
You can use the reinforcement learning for this matching problem. For you have minimize the distance. You can, for example.
No, you can speak in. Yeah, I said. Yeah, go ahead. Whatever language.
Par exemple, on peut faire le premier driver avec le premier taxi. On distance T plus le deuxième driver. On va choisir une distance T et on va multiplier par une alpha assez proche de 1. Puis le troisième driver, on va ensemble. Plus le troisième driver, on va alpha carré plus de T.
Okay, so let's I can try to be efficient in terms of replying to the questions. Reinforcement learning is another approach to think about problems where you are learning at the same time as optimizing. So learning, there is like something that there are some parameters that are in your problem that you don't know and that you are trying to learn them. Okay, so here typically there is no strong parameter that needs to be learned. So the distance is something that is known, right? But you might want to do learning, but not like in real time. You can revise the parameters of your model, but typically in this app, not in real time, not in second. Maybe at the end of the day, you want to revise the problem. But that's another approach. I'm looking to the time, and I think I will. You're gonna have time, so I'm gonna stay with you. I'm not going anywhere. You can have time to ask me more questions offline. Yes.
Juste une question.
Where are you? تفضل.
Juste une question. L'idée de voir une optimisation à 2 étapes,
ouais.
C'est assez récent, en 2021. Donc je pose la question, d'où vient la motivation d'essayer d'optimiser de cette manière?
Oh, okay. So the question is like, so 2-stage optimization is not recent, 3 years ago. So two-stage optimization in general, it started like people thinking about two-stage optimization, I would say 20 years ago. Two-stage, so it started mainly with two-stage stochastic optimization, and then I would say two-stage robust optimization came after that. The idea is that, you know, in science advanced, typically now we know how to solve static problems, a single-stage problem. So the natural question is like, with the existence of so many historical data that we can model uncertainty, let's look 2 steps further. Let's try to use what we can know about the future to optimize the present. And then the natural question is a two-stage problem. And then after that, once we solve that problem, we have a good understanding, we're gonna go to multi-stage problems. And in so many other applications, we know how to solve multi-stage problems, okay? So I'm gonna go to the second part of my talk, which will discuss stable matches. This is another class of matching. So if you slept so far, this is a good time to wake up. Okay, because we are switching topics. So you can forget what you've done in the first part and wake up and we're gonna start again, okay? You good? Let's go. So stable matches. So again, always we have a bipartite graph. Now the difference right now is that we have preferences, okay? We have preferences for one side over the other and vice versa. The classical application that started in the United States is how to assign students or med school students, okay, who are now struggling in this country, unfortunately. So how to assign them to hospitals. The way how the system works is the following. Each student has a list of preferences, okay? Each student has a list of preferences of the hospitals. And then hospitals as well do have a preference list over the students, okay? So for instance, if you take this student, it will be like, so I mean, when we say hospitals, they want to do they want to be resident, so residana, okay? So they take the exam and, you know, they might be admitted and then they put their preferences. Maybe some of you right now have to put their preferences for, you know, the engineering schools. But that's one side preference, right? The moment if you are admitted there and you choose it, you get it. Here, the hospital has to choose you back, okay? So the students, let's say this one has like the most preferred hospital where he want to be assigned is A, and then B, and then C, okay? And then hospitals as well do have a list of preferences. So A, you know, preferred the first student, and then the last one is the second choice, and then the third choice is this guy, okay? And at the end, you want to have a matching, which means each student will be assigned to at most one hospital in this example, and each hospital will admit at most one student. In this example, it's going to be exactly one because you have 3-3, okay? So we need an algorithm to solve this problem. This problem is also called the stable marriage problem, okay? Why marriage? Because another application that you can find that you can read in textbooks is that you can think about you have men on one side and you have women on the other side. And each man has a preference list over woman and vice versa. Each woman has a preference list over men. And you need to give a matching. But again, as we've seen in the previous problem, we ask the question, what is the objective function? What am I trying to optimize here? So this is why it's called stable marriage. So think about, you know, this is a Imlishil wedding festival. So you have the woman here, you have the men here. Each one has preference over the others, and this is the matching. Okay? But how do we do that? So we define a notion called blocking pair. So what is a blocking pair? This is the most important thing that you want to get from this part, the blocking pair. Remember that, blocking pair. So a blocking pair is when agents prefer each other to their current partners. So I and J, so I is from one side, let's say it's hospital, J is a student. I and J is a blocking pair if they prefer each other. They are matched to somebody, but they prefer each other over the current partner that they have. Okay? That means they have incentives to deviate from this matching. And the traditional objective function that one tries to optimize for is to have a matching where there is no blocking pair. That matching is called stable matching. When there is a matching without a blocking pair, we call it a stable matching. So let's do a simple example. Okay? We're going to do a simple example so that you wake up with the players. Who doesn't know these players? You don't know? Okay. This is Ziyech, Hakimi, and Unahi. And these are soccer teams. Chelsea, Bayern, and PSG. So let's do an exercise. So each player has preferences over teams. So Ziyech, the most preferred team is Bayern, followed by PSG, followed by Chelsea. For Hakimi, Bayern, Chelsea, PSG. Unahi, Chelsea, Bayern, and Paris. Okay? On the opposite side, teams do also have preferences over players. And these are the preferences. So Chelsea would rank Ziyech, Hakimi, Unahi. Ziyech, Bayern will start by Hakimi, Ziyech, Unahi, and then Paris has this ranking. We would like to design a stable matching. So each team would be paired with one player. Mercato. We want to design a mercato. Okay? Each team will be assigned to exactly one player, but we want the matching to be stable matching. Let me start with this example. Is this a stable matching? Chelsea, Ziyech with Bayern, Unahi with PSG. I'll give you time to think and raise your hand. Is this a stable matching? Yes. Yes or no? No. Why? Can you give it the mic because I have a difficulty?
For me, it's no, because if we see, for example, Bayern Munich, we have Ziyech is the third player that they want.
Yes.
And we pair it with Bayern Munich. I think that's not a stable matching, actually.
So the definition of a stable matching is a matching that has no blocking pair.
Yes.
A blocking pair is a pair where the parts of the pair, I and J, prefer each other to their current matching. So in order for me mathematically to tell me that this is not a stable matching, to give an example to tell me this is a blocking pair, or you tell me there is no blocking pair, please.
There is a blocking pair.
Yes?
Bayer prefers Hakimi, and Hakimi prefers Bayer. So they would rather change their clubs.
Wait, so Hakimi preferred Bayern to the current matching. He's matched to Chelsea, but he prefers Bayern. And then Bayern's preferred Hakimi to the current matching. So Hakimi and Bayern is a blocking pair, right? Hakimi is Bayern's blocking pair, so they're gonna deviate because they like each other to their current partner. So this is not a stable matching. Do you have another example?
I think it's a stable matching because in each pair.
I just showed that this is not a stable match.
No. I'm sorry.
Okay. You buyer to the current matching, which is PSG. So the moment, the men and women like each other, think about it, woman and men is easy, like each other to their current partner, it's not stable. It's a blocking pair. The matching is not stable. Okay? This is a stable matching. So in this example that I'm giving you here, you're not going to be able to find. The question, can we always find a stable matching? What do you think? Can we always find a stable matching? Yes or no? Yes.
So, if I'm okay, I think it's
not in this example. I'm saying in general.
Yeah.
Here I gave you already. Yes, you are saying
it's possible.
Yes.
Thanks to if my memory is good.
Yeah.
Gale-Shapley algorithm.
Thank you for introducing my next slide. This is a Nobel Prize 1962. There exists an algorithm that solves the stable matching. Actually, in polynomial time, there exists always a stable matching. Okay? What time is it? Wow. So let me give you a glimpse of this algorithm. Let me tell you a lot about this algorithm. So I'm going to use again men and women. You have a bipartite graph with men and women. Each man has a preference list. So you rank the women, and then the same thing for each woman ranks the men. And the goal is to find a stable matching, a matching where there is no blocking pair. The algorithm, there exists an algorithm. It's called the Gale-Shapley algorithm. That's your friend. What's your name? Adam just mentioned. It's a very famous algorithm. Any one of you who study operations research or computer science, applied math, would see that in a master's course. So the algorithm is very simple. It works like this. I'm not going to go through the proof of the algorithm because of the limitation of time, but I will give you an idea about the algorithm. So you proceed in rounds. What you do is in each round, you start with men. If you can start men and women, just you can start with any side. Let's say, for simplicity, you start with men. So the man proposes to his highest ranked woman who has not rejected him yet. You have a question? Yeah.
Je me demande juste, est-ce qu'il y a une relation entre ce théorème
Hall's theorem. Yes. That's another proof. So yeah.
Okay.
Yeah. So let me continue with this algorithm. So the man proposes to his highest ranked woman who has not yet rejected him. Okay. So you're gonna select a man, look to the preference list, and he will basically proposes to the highest one. So the woman accepts any proposal if it's preferred to their current matching. Okay. So let's say at some point, the woman gets a proposal. She would just compare the current matching with the request. If the request is better, bye-bye to the current matching, we'll accept the new request. You run this algorithm in at most n square iteration, you get a stable matching. So some of the ideas of the proof. So once a woman is matched, she stays matched because she always prefers to be matched than being unmatched, and she always only improves the matching. The men can be matched, but then can be rejected at some point, and then we'll ask again another woman, and eventually every woman will be matched and every man will be matched. And this algorithm is polynomial time, is very efficient, is one of the beautiful, I would say, beautiful algorithms that have been developed in this area of matching. This was the end of my second part. Because of the time, I'm gonna try to be quick in terms of the last part. Trying to spend less than 10 minutes here so that I can give you the opportunity to ask any questions that you might have, okay? So in the last part, I'm gonna talk about two-sided assortment optimization. Let me explain to you what is that. So in the two previous examples, what you've seen is you have a bipartite graph, you have supply and demand, and then the decision maker, which is typically the platform, the marketplace, which is Uber, which is like the organization that does the assignments of schools and hospitals and students, like the Mercato, who assigns players and students. So they control the match, players and teams. They control the matching. They tell you, let's match I and J. In many other applications, you don't control the matching, but you control what you offer to the agents. Mathematically speaking, you have a universe of items or options. You need to find a subset of those options to offer to the agent, to the player, to the client. The client will click on something according to some distribution, and then the matching is generated. So you don't say I is matched to J when you solve, but you say, for I, I'm going to show these options. And then let's I chooses. When you decide what you offer to the agent, this is called an assortment problem. This is an area that's called assortment optimization. And there are so many applications here. For instance, these accommodation platforms like Airbnb. You decide what accommodation you're going to show, the client will choose. Dating apps, some of you might be using this. You decide the subsets that to display and you choose, right? You might get match or not. Carpooling, outsourcing apps. There's a lot of new apps here. That's you have firms and you have freelancers. The platforms will show some subset of projects to the client. The client will choose something, and then the client is the freelancer. The freelancer will choose some project to work on, but the project has also to be chosen by the freelancer in order to generate a match. So what is controlled here is the subset that you show. So I'm going to skip this and directly go to the model. So the model is the following. Again, I have a bipartite graph. For simplicity here, I'm going to call it customers and suppliers. So you have two sides, customers and suppliers. What is my decision variable? What do you control? You control what you offer to the suppliers. So let's say I offer this subset. There is a probability distribution that is typically known in the literature, a choice model, that will tell you what is the probability that I will select each of these options. So, and I might also not like anything here and will leave without choosing anything. And then the same thing, you control what you show to the supplier. You're going to offer an assortment C, a subset C to the supplier. Supplier J might leave with this probability and might choose each of the agents in the C with some probability phi J I C. And if two agents chooses each other, then there is a match. Okay? That's a match. You would like to maximize the expected number of matches. Okay? So you would like to decide what assortment, what subset you want to show depending on this probability distribution so that you maximize the expected number of matches. Of course, this will depend on each application. This is going to depend on the design of the problem in terms of the sequence of interactions. Who started first? To whom you're going to show the first subset, right? So in some application, you might show everything at the beginning and let them choose each other, and then you generate the match. In some other, you fix a side, let's say in accommodation, only the client side will make the choice first, and then you go to the other side. So there are different, and for each design, there is a problem, an optimization problem that needs to be solved, where we need scientists and a mathematician to solve this problem, the design algorithm to solve the problem efficiently. So let's finish with, so there are so many designs. Let me finish with a simple example with what I'm going to show you that the design matter, the sequence of interactions matters. So this is a toy example. This is going to be my last example. This is a toy example. You have two customers, I and I prime, and you have one supplier that is called J. The probabilities are the following. So for the customer, there is only one option, which is this supplier J. And if you show that option, I will choose j with probability half, and will leave with probability half, right? So phi ij is half, and will go out with probability half. Same thing for I prime. If you show j, I prime will choose j with probability half, and will leave with probability half. Now, what is the probability distribution for j? For j, well, it depends on how many customers you are showing. You can show one, you can show both of them. So if you show one, then the probability is 1 over 1 plus the cardinality of the size of the set that you are showing. So if you show one, it's 1 over 2, that j will choose I, and j will leave with probability 1 over 2. But if you should show both of them, j will choose I with probability 1/3, because the cardinality right now is 2, and j will choose I prime with probability 1/3, and will leave with probability 1/3. Let's look to these two simple policies. If I show everyone everything, how many matches in expectation I can have? Well, these are the probabilities that I have. So j will choose I with probability 1/3, will leave with 1/3, which is I prime with 1/3, and I prime both either leave with probability 1/2 or choose j with probability 1/2. Expected number of matches, well, there is a match in here with probability 1/3 times 1/2, that's 1 over 6, and there is another match in here with probability 1/2 times 1/3, that's 1 over 6. The sum is 1/3. So with this policy, what I'm showing everything, everyone, or everyone, everything, the expected number of matches is 1/3. Let's look to another policy. Let me start with one side. Wait, I'm going to start with one side. I start with customers. I show them j. If both of them choose j, I will offer both of them to j. If only one of them choose j, I only offer that one. So this, as you can observe here, I'm introducing something called adaptivity. Is that I'm learning I'm getting some feedback from the customers before I process. So this is an adaptive algorithm, and it performs better than the other one. Actually, if you do the math here, you're going to find that the expected number of matches in the second policy, where I'm adaptive, is 5 over 12, which is strictly greater than 1/3. I might have lost you through the details of this example, but the idea that I wanted to convey here is that adaptive algorithms do better than static algorithms. And that's what we showed in this example. There are so many algorithms and so many problems here in this. This is a very nice literature. There is very nice body of work. If you are interested in this, so I've just written a recent paper on two-sided assortment optimization for people who want to, kind of discover this type of problems. All this, I mean, you can take a picture if you want, but as well, all the papers, you can find them on my website and some other research topics. This is my email if you have any questions. Thank you very much for your attention, and I think we're going to do questions. Okay, thank you.
Yeah, thank you very much, Professor Housni, for this amazing talk. I think all of us learned a lot about matchings today, and hopefully some of you are going to be inspired by this talk to work in the field of operations research. Okay, we have a few minutes, so we're going to start taking questions. So we'll have 2 mics, and we'll go around taking questions. So I have a question there to start with.
Merci de passer rapidement. Après, ma question est, est-ce qu'on peut connaître à quel point on a pu optimiser notre problème qu'on veut résoudre? Et ma deuxième question, je me demande, est-ce que lorsqu'on écrit un code, y a-t-il un moyen qui montre qu'il est exact et qu'il ne fait pas d'erreur, ou on teste juste des cas comme ça?
Okay, so the first part of the question. So when you design an algorithm, if you just give me an algorithm without a proof, that is called a heuristic. So there is no theoretical guarantee there. You just tell me, hey, if you want to assign drivers, do that. Solve this, do that, take the square, whatever, took this step. But when we try to design an algorithm, we always think about the theoretical guarantees. So that when I say the theoretical guarantee, so either you tell me this problem is gonna, so you show it mathematically, this problem is gonna solve the problem to optimality, right, in polynomial time. Or if it is a, not to optimality, you give me a theoretical guarantee, which means that, let's say it's a minimization problem. You say that my algorithm gives you a 2 approximation solution, which means the output of the algorithm in the worst case is not more than twice the optimal objective function. If the optimal objective function, let's say it's 10, and you tell me your algorithm gives you 2, that means in the worst case, you're not going to be more than 20. In order to test the algorithm empirically, so like you just need to run experiments to test the performance of the algorithm. I think for the second question, I could not get mainly the second question, but we can talk about that offline so that we can give opportunity to other students to ask questions. Okay, thanks.
Hello, sir. Thank you first for your presentation. I just want to ask you, why can't we implement machine learning and like use neural networks where weights are those sets of values of xigs, and then use back propagation to find the right set of xigs values to solve the first problem that you have presented?
Okay, so there are 2 types of research areas here. So there is something called predictive analytics, and there is something called prescriptive analytics. So predictive analytics is when you're trying to predict a value or some parameters of the problem. And that's where machine learning plays a role, okay? Or deep learning is when you're trying to predict something. You want to learn some parameters. You want to know what's the value of the stocks tomorrow, right? So that's machine learning, okay? Then when you learn these values, you need to take decisions, right? To take decisions, that's called prescriptive analytics, and in math it's called optimization, okay? So do not confuse the 2. So here in the matching problem, you need to make a decision. The decision is like a matching, so you need to solve an optimization problem. Typically, to solve this type of problems, you do the first part. The ways you can use machine learning, I said that in my talk, to learn the weight of the problem, right? But once you have this is the first. So usually these 2 things are coupled, right? If you want to solve a problem, you want to learn some parameters. So the weight, you might want to forecast, let's say, one of your friends say there is a traffic between I and J. So you don't know what's the traffic. You may use historical data and tell the machine, the ML algorithm, give me what's the distance between Bij, right? Using historical data. But once that gives you, there's a whole a problem that still needs to be solved. And to finish my answer, sometimes you might ask also the machine learning or like the neural net to take decisions. But the problem with that in general is that this is not explainable. So it will give you a decision, but it won't tell you when it fails, it won't tell you why. Because it's a black box. That's why it's ML, it's a black box thing. Why here you know exactly what you are. You put your objective. You say, I want to minimize the distance. I want to maximize the weight. I want to have a stable matching. You have something that is interpretable. Okay? So that's the main thing, the difference between these 2 areas. Yes?
First of all, I would like to thank you for the presentation. It was very instructive and useful. My question is concerning or regarding the stable matching, the marriage.
Yes.
I would like to ask if the stable matching is compatible with the Islamic instructions in which a man can be or matched with at most 4 wives. And more seriously, I would like to ask if the stable matching is compatible with the choice of the grandes écoles in the SEI platform. Can we match or have a stable match to a school in which we can have at most a certain number of students that can be matched to it, knowing knowing that these students prefers a certain school to another, in which I would like to ask if the fact that we had one wife to one man, or woman to one man, is the same thing as having a lot of students to a school.
Okay, so I'm gonna skip the first question. So men and women here is just something in textbook that has been used for this class of problems, stable matching. The goal at the end is to have a matching. The definition of the matching that I had in the first slide is that each agent can be matched to at most one agent on the other side. That's the definition of a matching. Other than that, it's not a matching. We need to find a new name for that. For the second thing, can the admission between engineering schools and students use the stable matching algorithm? Yes, in principle, but that's not the way how they work. So yes, in principle, because each student might have a preference list, right? And the schools do have as well preference list, which is just the ranking of the students, but their goal is not to have a stable matching at the end. So the way how they process is like, they give the student the choice, and they have waiting lists. So they don't do sequentially, like going student by student, hey, you choose, and then, or like basically the school chooses. So they whoever gets admitted, they can join the school, and then if they have more spots, they go to waiting list. So the stable matching is more used in this assignments of resident students and hospitals in the US, as well as also some like families, also in some primary schools in the US. There's like a lot of research that has been done. The one thing that I want to mention, this is not the only problem. This is the classical problem. This problem dates from 50 years ago, right? There are so many right now constraints that's on the top of what I presented today that can be incorporated. So there are so many fairness constraints that can be, and so many dynamics that can be studied within this class of problems. Yeah. Bonsoir.
Merci bien pour cette excellente présentation sur la théorie. Merci pour cette excellente présentation sur la théorie des graphes. Nous avions suivi une présentation sur la théorie des œufs. J'ai remarqué qu'il y a une similarité entre ces deux domaines. Là, je voulais comprendre, est-ce qu'il y a...
Présentation d'hier de M. Reda Al-Iraqi, théorie de jeu.
Oui.
OK.
Je voulais comprendre, est-ce qu'il y a une collaboration dans ces deux domaines dans les entreprises? Parce que j'ai remarqué que votre présentation est basée sur le codage, comment optimiser à partir des machines, avec des algorithmes pour optimiser alors qu'avec la théorie des jeux, il y a plus quelque chose de mathématique. Les conférenciers avaient parlé qu'on appliquait ça plus dans l'économie. Je voulais savoir, est-ce qu'il y a une
Très bonne question, très bonne question. Je vais répondre. So there are similarities and there are differences there. So in game theory, you have players, right? And players can be adversarial. So you might have player 1 takes an action, player 2 can be adversarial, right? And then player 1 could take a following action, and there is a game that happens between the players. So this aspect of being adversarial, you can see it in my presentation when I was talking about robust optimization. So I was saying, like, I would like to hedge against the worst case in the objective function. So who are the players there? The first player is me as a decision maker. I'm the one solving the optimization problem. The second player is nature. So nature is, is the worst case, right? So you're kind of playing against nature, right? You hedge against the worst case. You say, I'm going to assign this driver to riders. Maybe in the worst case, nature will choose that the next request is gonna be like, not in my favor. It's gonna be really bad for me. But the difference is that typically in game theory, the objective functions are different. So game theoreticians, they usually look for Nash equilibrium, right? I guess you've seen that yesterday. Okay. So here we in the objective function, so we define our objective function. We're not looking for in the robust optimization problem to find a Nash equilibrium. It was like, a worst case objective function. But also you can have as well some interpretation of the stable matching, that because of the blocking pair is two people, when there is no blocking pair, there is a stable matching, people do not want to deviate. So you can think about the connection to Nash equilibrium where no agent wants to deviate from their current actions. Yeah.
Well, thank you very much. Let's thank Professor Omar Housni one more time. Thank you. So unfortunately, we're running out of time.
Can I say one last word?
Of course you can.
Yeah. So I know that a lot of you wanted to ask questions outside of the topic of the presentation, mainly about like some orientation questions. I'm staying here overnight, so I'm gonna have dinner around. So I'll be around if you want to talk to me in person. If you have any questions, orientation, PhD research. The goal of my presentation was mainly to inspire you, inspire the Moroccan young mathematician to pursue research and do PhD in areas. So each time I give a talk, I try to find or to speak about something different, so that you can have exposure to so many topics. So yeah, I'm gonna be around. If you have any questions, it's gonna be my pleasure to respond to these questions. And thank you very much for your attention. Thank you.
Ok, so, donc comme vous le savez, on a lunchbox dinner aujourd'hui, et ensuite il faut aller au CCI. Donc il faut que vous soyez il faut que vous récupériez votre lunchbox au resto à 18h30, donc dans pas longtemps. Et s'il vous plaît, ne soyez pas en retard. C'est une contrainte, ça va être constraint. Il faut récupérer votre lunchbox à peu près 18h30. Et ensuite, vous allez directement au College of Computing. C'est là-bas qu'auront lieu la suite des activités. Je pense que